In this video, we're going to look at sections 8.4 through 8.6. So in section 8.4, we're going to talk about how to detect unequal variances. So this is the next assumption that we're going to look at, and if you'll recall, one of the assumptions we have is the one where we have to have constant variance for all levels of the independent variables. And so variants that have this property are what we call homoscedastic, whereas unequal variances for different settings of the independent variables are said to be heteroscedastic. So when the data are not homoscedastic, or we could say they're heteroscedastic, the reason is often that the variance of the response y is a function of its own mean. And so we've got a couple different examples we're going to look at here. So the first one happens if the response y is a count that has a Poisson distribution, then the residual plot will resemble the following. And so notice here it's kind of rounded and then it comes out. Now the reason that this is not homoscedastic is if we notice here the y-hats have very small variability, whereas out here they have very large. So we don't have equal variability as we move out. And so cases where the response y might be some kind of count that has a Poisson distribution, an example of that is maybe we want to figure out how many people are entering a store during a given hour of time. And so notice, you can't have negative people enter a store, you can't have half a person enter a store. That can range anywhere from 0 up to however many. And so that would be reasonable to model that with a Poisson distribution. And so in cases where this happens, what we can do is we can use a transformation to help us. And what we'll do is instead of working with y's, we transform the y to the square root of y. If the responses are proportions that were generated from a binomial experiment, then the residual plot will resemble, it looks kind of like a football. And so here's the football shape. And notice here and here we have smaller variability than we do in the middle. And so in cases like this is the transformation that we tend to use. And then a third one that we could look at is if the random error component has been assumed to be additive for all the models that we have constructed. In other words, what we're saying here is the expected value of y plus epsilon gives us y. However, if the model is really multiplicative, and so by multiplicative we mean that y is equal to the expected value of y times epsilon instead of plus, we end up with plots that look like this. And so notice this one it's similar to this one, except instead of that growth being curved, it's more of a straight line. And in this case here is the transformation that we can use. In general, for most of these residual plots that we build, we're looking for some kind of pattern. These are not the only patterns that you could see, but these are just some common patterns and some ways that we could transform the data to take care of that. So let's look at an example of this. So here, in our example, we have data on age, which is an X in years, and plasma levels of a polyamine Y for a portion of 25 healthy children in a study. And so notice here, we're going to use age as our X, and Y is our plasma level. And then here, we've got the natural log of Y, and we'll need that here in a little bit. All right, so what we're first going to do is we're going to just consider that straight line model that we've seen before, just our simple linear regression, and we're going to use age to predict plasma level. So here is that fit using Minitab, and let's look at some of the regression analysis. All right, so we're going to focus on this bottom plot, and notice what we've got here is we've got age and then we've got our residuals. So notice here at age 4, we've got smaller variability compared to age 0. So since age is our explanatory variable, what we are finding is that the variance of that residual, and remember the variance of the residual helps us estimate the variance of the error term, we find that that variability is larger for low ages versus the higher. So in other words, this would suggest heteroscedasticity. One thing to notice here is we have kind of a rough megaphone shape. And so what I mean here is we're smaller on one end and larger at the other. So what we've got, again, is smaller variability for larger values of age. And the shape that we're seeing here, we call this a megaphone shape. All right, and if we go back to page 9, notice here we can see, here's where that megaphone shape was, and one of the suggested variance stabilizing transformation is that of natural log of y. So what we've done here is we're going to try the logarithmic transformation on the response variable. And so again, here is that fit in Minitab, but notice we fit it using the natural log of plasma instead of the regular y that we saw before. And if we look at those same plots, notice that this looks much more homoscedastic than the plot that we saw before. Now we do need some cautions when using transformations. So notice if we use this regression model, it's going to predict the natural log of y, and it does this by using ln y hat. Consequently, the predicted value of y is now the antilog. So we can transform the endpoints of prediction intervals back to the original scale, and the interval will retain its meaning. However, you cannot take the antilogs to find confidence intervals for the mean value, the expected value of y. The reason this is true is that the mean value of the natural log of y is not equal to the natural logarithm of the mean of y. In fact, the antilog of the logarithmic mean of a random variable y is called its geometric mean. And so suppose with 95% confidence we wanted to predict plasma levels for a healthy child who is 3 years old. So notice here at the bottom I've got the confidence interval. This was fit using the natural log of plasma, so we've got the confidence interval and we've got the prediction. So what these cautions are saying is this one right here we can't transform. But this one, the prediction interval, we can transform. Now our question is asking us to predict the plasma level for a healthy child, so we do want a prediction interval here, so we're fine to answer this problem. So notice our interval, what we're going to do is we're going to take the antilog of the two endpoints here, and this will give us back in terms of the y that we want. So our interval we're going to have is going to be e to the 1.60009 e to the 2.21285. And this is equal to 4.95 to 9.1417. And then we can interpret this the same way that we've interpreted prediction intervals before. So we predict with 95% confidence the plasma level for a healthy child who is 3 years old will be between And then it's always good when working with transformations, just to double check that nothing went wrong. Always go back to your original data set and say, hey, does that value even seem reasonable? And so what we're going to do is let's go back and look at our original data set. So our prediction is somewhere from about 5 to 9. And so if we go back and look at our original data set for our 3-year-old children, notice that, an interval from 5 to 9 based on our data seems pretty reasonable. Whereas if I had gotten a prediction interval, let's say was from 12 to 20, I might say, hey, I think something's gone wrong here, and I would go back and check. And then again, just to emphasize here, remember, you can do this for the prediction interval, but you cannot do this for the confidence interval. And again, the reason for that is that if you take the mean of the natural log of y, that is not equal to the natural log of the mean of y. And confidence intervals are in terms of the average, what is happening on average. There are hypothesis tests that you can perform to check whether or not you have heteroscedastic variances. So in general, plots help inform us of what's going on, but it's always good to do hypothesis test. And so there are many hypothesis tests that you can use. However, one thing to keep in mind is all of these tests assume that the errors are normally distributed. In most cases, the graphical procedures are sufficient to assess whether or not they are homoscedastic. And so we're not going to cover those tests those test procedures for equal variances given in this section. But do know that they are out there, and you can use the graphs or plots, but you always take those with a grain of salt. In practice, I look at plots all the time to decide whether or not assumptions are reasonable, but in the back of my mind, I also know there are hypothesis tests to help me check those. All right, so in the next section, we're going to look at checking the normality assumption. I'm going to let you read this section on your own. I don't really have too much to add to it. You'll find that most of these are similar to when you checked normality when you were just working with a single variable back in your intro stat class. So if you'll remember, there were certain plots that you could look at. You can make a histogram, see if that looks approximately normal, stem and leaf plot. There were different things that you could look at there. So I'll let you read that section on your own. Our next section, 8.6, it looks at detecting outliers and identifying influential observations. So an observation with a residual that is larger than 3 standard deviations in absolute value is considered to be an outlier. And so we could ask ourselves, well, where does that 3 standard deviations come from? Surely they didn't just pull that out of nowhere. And we should all know that the answer is they don't. The reason we're looking at 3 standard deviations in absolute value, this comes directly from the empirical rule. We're making this assumption, this normality assumption, and so as long as that is valid, it's reasonable to think that all the observations, that all the residuals, not the observations, all the residuals should be within 3 standard deviations. So in order to easily check to see if an observation is an outlier, we define what we call the standardized residual. And so the reason we do the standardized residual is because we can compare that to a standard normal. And so if the standardized one is larger than 3 in absolute value, then we know it's an outlier because, again, based on the empirical rule. So notice here when we calculate the standardized residual, one of the things that we know is that the expected value of our residuals is 0, or of our error terms is 0. So really what we're doing here is we're taking our residual, we're subtracting off the mean from the errors and dividing by the standard deviation. So this really is the value minus the mean divided by the standard deviation. So that does come from a standard normal distribution. And then outliers are usually attributable to one of several cases. It may be that the measurement associated with an outlier may be invalid. And so when this happens, it may be this experimental procedure used to generate measurement may have malfunctioned, the experimenter may have recorded the measurement incorrectly, and data may have been coded incorrectly for the entry on the computer. In practice, if I know that there is an outlier due to somebody entering the wrong value, I will remove that outlier, but I make sure in my documentation I'm very clear and say, hey, I removed this outlier because somebody hit a couple extra zeros when they were entering or something, so I know this data point is not valid. We never remove data points from an analysis without documenting it. So documenting it is incredibly important in analyses. We always want to be very clear about the steps that we took. So even if it's an obvious, error, you can't just take it out and ignore it. You can take it out, but make sure you document what you did. Outliers may be due to skewness, non-normality of the probability distribution of the random error, chance, or unassignable causes. Now, when this happens, I'm really hesitant to remove outliers from my analysis, and the reason that is I might need to take that skewness into account when I perform my analysis, because that's an actual phenomenon with the data itself, and so I don't want to ignore that is happening. The outlier may be the result of an omission of an important independent variable or higher order terms. And there are several formal techniques we can use to identify influential outliers, and we're going to look at those. And then as an alternative to standardized residuals, some software packages compute the studentized residuals, so named because they follow the approximate student-teased distribution. And sorry, you can hear my dog in the background. So this is very similar to what you saw in your intro stats class when you could work with a standard normal distribution or a t-distribution. It's two different ways to approach looking at the residuals. But in either case, really what you're doing is you're transforming them to a known distribution. It's a distribution you know how to work with. We know how to work with standard normals. We know how to work with t-distributions. And we can use those values to very quickly see if those values are falling far out into the tails of either of those distributions, which would help suggest that they are outliers. All right, and so here is the formal definition of the studentized residual. And again, we do denote it zi star for the ith observation. Now the h that is in here, you do need a computer to calculate h. I'm not going to make you calculate those by hand. You are going to get those in computer output. The leverage of an ith observation, we can think of it as its weight, that is the hi associated with the ith observation. And so here what we can think of is y hat I as this weighted average of all of the individual y's, and the h tells us what its weight is. And again, we're going to use computer output to calculate these for us, but you can imagine if h is high for a particular y, what this is telling us is there is a lot of weight associated with it. So high h's or high leverage tends to tell us that value or that observed value of y is influential. And here is the rule that we use to determine if hi is high. Another technique for identifying influential observations requires that you delete the observations one at a time, each time refitting the regression model based on the remaining n-1 observations. This is based on a statistical procedure which is called the jackknife. Deleted residual, denoted di, is the difference between the observed response yi and the predicted y hat I. And it's obtained when the data for the ith observation is deleted from the analysis. And so here is the definition of di. And then finally, also we're going to look at Cook's distance. So Cook's distance is a measure of the overall influence of an outlying observation. And it has on the estimated beta coefficients, so that's a beta there, was proposed by R.D. Cook in 1979. And so here is the formula for di. And a large value of di is going to indicate that the observed value y has strong influence on the estimated beta coefficients. So again, I'm not going to ask you to calculate the di's by hand. The computer output is going to do that, and we're going to look at an example here in a second. But your goal is to look at the di's and decide, is that value high? Is this potentially an influential point? And then again, here's that studentized idea again, but now this is the studentized deleted residual. All right. So we're going to look at an example here of how we could use all of these things to determine if points are outliers and if they are influential. All right, so we're going to look for influential observations. So here is our data set number 1. So data set number 1 that we're going to start out with here, it has 20 observations. And what we're going to do for data set 1 is we're going to start with 20 observations. We're going to see what the data looks like, what our fit looks like, and then we're going to look at a couple data sets after this where for each one of those data sets, we're going to add in an observation 21. And what we're going to see is we're going to add that observation in, that observation 21 at different points, and to see as it gets extreme in different directions, what is happening. All right, so here is our output for this data set 1. And then afterwards we have the fit and diagnostics for all the observations. So again, notice that this goes down to observation 20 because we had 20 observations for data set 1. And then this second part down here, it's just the table couldn't fit all the way going this way, so it just got moved down. So these are the same, still the same 20 observations that we have up above. Now that Durbin-Watson statistic that's there at the bottom, we're going to look at that when we get to section 8.7. All right, so looking here, let's identify some different pieces. Deleted residual, that's our DIs. HIs, that is our leverage. We've got the standardized residual, that's your ZI. And then we've got your residuals, which is your epsilon hat I. Then you've also got your Cook's D down here. All right, so we're going to look at all of these and kind of determine if we've got any high or low points, probably not high or low, but any high points to determine if any of these are, influential points that we need to be concerned about. All right, so the first thing we're going to do is we're going to look at our H's. So remember that we consider HI to be high if it's greater than 2 times k plus 1 divided by n. Right? So in this case, that is going to be equal to 2 times 1 plus 1 divided by 20. And so let's review, why is it that we've got k plus 1? Well, the reason we did this is because we've only got a single predictor. If we go back and look at our output here, notice we've only got a single predictor. So that's why k is equal to 1. And so that is equal to 0.2. All right, so if we go through, and what we're going to do is we're going to look at all of our HIs, and we want to determine are any of our HIs greater than 0.2. So take just a moment and see if you find any that are greater than 0.2. So notice there are no observations that meet this criteria. So we don't have any evidence that we've got a leverage point in this case, or a high HI. Now we could also look at our standardized residuals. So remember, those are right here. And by the empirical rule, we're looking for an observation that is greater in absolute value than 3. So notice all of these are within 3 observations. So here we're good. Now one thing to notice about the standardized residuals here, you do want to take into account the number of observations that you have. If I have 1,000 observations, by the empirical rule, 99.7 should be within 3 standard deviations. So if I had a data set with 1,000 observations and I found 2 of them had standardized residual 3.25 or maybe 3.4, I'm not going to be too worried about those points. So again, keeping in mind that that 3 rule comes from the empirical rule, and you do want to kind of keep in the back of your mind, how many observations do you have? All right, we could also look at Cook's D. So notice Cook's D is right here. So for Cook's D, a large value of DI would indicate that the observed values YI had a strong influence on the estimated beta coefficients. So the values of DI, how we figure out if they are large or not is we compare them to an F distribution. So kind of recall here that F distributions, those are a right skewed distribution, so they look something like this. And if you'll remember, F distributions have two different degrees of freedom associated with them. So for this F distribution for Cook's D, our first degree of freedom for that F distribution is going to be equal to k plus 1, which again is 1 plus 1 in this case, and nu2, or our second degree of freedom, our denominator degree of freedom for our F distribution, that's going to be given by n minus k plus 1, or in this case that is going to be 20 minus 2, which is equal to 18. So then what we do is we look for the 50th percentile of the F distribution with those 2 degrees of freedom. So in other words, we're looking for the end point which has 50% of the area below it. And it ends up for this particular F distribution, that value occurs at 0.721. So we're looking for Cook's D which are larger than that value. Now we don't have any values of Cook D larger than that value, so in this case, again, Cook's D is not indicating here that anything is influential or there's anything that we need to worry about. Now what we're going to do for data sets 2 and data sets 3 is we're going to add on a 21st observation. And so if we look at data set 2, if you compare this with data set 1, so here's data set 1, notice this is our new data point. So we're adding in that data point. And what we're going to do is we're going to look at the output for this 21st data point and see what happens. Then for data set 3, notice we've added in this data point. And then again, so that's, we don't have this point here. We still just have 21 data points. It's just now that's the 21st one that has been added on. And then for data set 4, we've added on a point here. So notice for each of data set 2, 3, and 4, what we've done is we've added on a 21st point, but we've made them extreme going in different ways. One of the extreme ones, well, if we look here, notice this one is extreme in terms of x. It's further apart than any of the observed x's we had before. For data set 3, this point is extreme both in x and in y, but follows along with the overall pattern that we saw. And then for data set 2, this one falls outside of the overall pattern. So it's not extreme in x or y, but is outside of the pattern. And then again, what we want to do is look at what are these values for this 21st point. So if you will turn to page 24, I have typed up what that summary is. So you'll notice here for data set 1, this is exactly what we just talked about. I've repeated this for data sets 2, 3, and 4, talking about where we've added in that 21st point and what is happening to these different values. So I'm going to leave you to read those on your own and to look over them. And that's going to conclude the section 8.6 video.